Howdy. This video is on oxidation states, formal charges, and exceptions to the octet rule. Oxidation states are used to track electrons to tell which atoms lost or gained electrons during a reaction. Formal charges are used to tell which Lewis diagram is the most stable. The closer to zero for the formal charges, the more stable. Often, formal charges are a better criteria than noble gas configuration for determining what's the most stable Lewis diagram. Using formal charges, we can also understand why there are exceptions to the octet rule. So after watching this video, you should be able to determine the oxidation states and formal charges of atoms and molecules. You should be able to use formal charges to determine which resonance structure is the most stable or which isomer is the most stable. You should be able to use formal charges to understand why there are exceptions to the octet rule. So atoms and molecules are often characterized by their oxidation state and by their formal charge. Oxidation state, oxidation number, I'll use those two terms interchangeably, is the charge an atom would have if the bonds were purely ionic. Formal charge is the charge an atom would have if the bonding electrons were equally shared. And so we can determine oxidation number by taking the number of valence electrons the atom has by itself minus the number of valence electrons in the bound atom, with the bonding electrons going to the most electronegative. Now in a compound, typically alkyl metals have a +1 oxidation state, alkaline earths +2, oxygen -2, and fluorine -1. And so if we look at water, and if we want to determine oxidation states, we imagine the bonding electrons going to the most electronegative, which in this case is oxygen. And so oxygen starts with 6 valence electrons for an atom, -2, 4, 6, 8. And so we get a -2 oxidation state for oxygen. Hydrogen, it has a single electron when it's an atom by itself. Now with the bonding electrons to the oxygen, hydrogen now has 0. 1 minus 0 gives us 1. And so oxidation state of oxygen in water is -2. For each hydrogen in water, it's a +1. The sum of the oxidation states equals the net charge. Now water has no net charge, and so the sum of the oxidation states equals 0 in this case. And so when we're thinking about noble gas configuration, we're seeing how many electrons each atom sees. So we see hydrogen sees 2, which is noble gas configuration for it. Oxygen sees 8, which is noble gas configuration for it. In terms of oxidation state, we imagine the bonding electrons going to the most electronegative. Formal charge, it looks very, very similar. We have the number of valence electrons of the free atom minus number of valence electrons in the bound atom, but this time the bonding electrons are equally shared. That's why we say the oxidation state is the charge an atom had with the bonds were purely ionic. Formal charge is the charge an atom would have if the bonding electrons were equally split. And so if we want to get, so we did the oxidation state for the atoms of water. If I want to do the formal charge, we now imagine that these two bonding electrons, one goes to the hydrogen, one goes to the oxygen. For these two bonding electrons, one goes to hydrogen, one goes to the oxygen. Now again, we have number of valence electrons for the free atoms. So for oxygen, that's 6 -2, 4, 6. And so we get a formal charge of 0. For hydrogen, it starts with 1 -1. Formal charge is 0. And again, formal charges of 0 indicate stability. And again, just like for oxidation state, the sum of the formal charges equals the net charge on the molecule. And again, when you're doing noble gas configuration, you're looking at how many electrons the atom sees. When you're doing formal charge, you're splitting those bonding electrons equally between the different atoms. And so for carbon dioxide, if you want to do oxidation state, again, we imagine it ionic. And so oxygen, we get all the bonding electrons. And so we'd have 6 -2, 4, 6, 8. And that gives oxidation state of -2 for oxygen. For carbon, 4 -0. And that gives us a +4. For the formal charge, 2 lines correspond to 4 electrons. So 2 goes to the carbon, 2 goes to the oxygen. 6 -2, 4, 6. That gives us a formal charge of 0. For carbon, 4 minus 4 gives us a formal charge of 0.
Formal charge calculations can often help us identify the most stable isomers of molecules. Consider the isomeric compounds, hydrogen cyanide and hydrogen isocyanide. Both structures have octets of electrons about carbon and nitrogen. The formal charge on carbon in hydrogen cyanide is 0. Similarly, the formal charge on nitrogen is 0. In hydrogen isocyanide, the formal charge on carbon is -1. The formal charge on nitrogen is +1. Because the formal charges are non-zero in hydrogen isocyanide, we can predict that this isomeric form is less stable than hydrogen cyanide, as found to be the case.
And so isomers can have just different arrangements of atoms. And so structural isomers, different arrangements of atoms. And so for hydrogen, carbon, nitrogen, we can put carbon in the middle, or we can put nitrogen in the middle. And so the question would be, how do we know which is the more stable structure? These are just two isomers. Now, if we look at the noble gas configuration, hydrogen's got 2, carbon 8, 2, 4, 6, 8, nitrogen surrounded by 8, 2, 8, 8. And so based on noble gas configuration, they both should be equally stable. But based on formal charge, 1 minus 1 is 0, 4 minus 4 is 0, 5 minus 1, 2, 3, 4, 5, 0, 1 minus 1, 0, 5 minus 4 plus 1, 4 minus 5 gives you a -1. And so we want 0 formal charges. That means this one's going to be more stable. And so we would predict that in this molecule, carbon should be in the center. The predominant structure is the one with charges as close to 0 as possible. And again, a structural isomer, you have the same set of atoms, but a different arrangement.
Formal charges can also be helpful in evaluating alternative resonance structures. Let's consider nitrogen dioxide, a molecule that contains an odd electron. We can draw 2 reasonable Lewis structures, but which more closely describes the nitrogen dioxide molecule? Notice that in one structure, the unpaired electron is on oxygen, and in the other, it's on nitrogen. In the first structure, the formal charges on all the atoms are 0. In the second structure, nitrogen bears a formal positive charge, and one of the oxygens bears a formal negative charge. Nitrogen is less electronegative than oxygen. Nevertheless, a formal positive charge on nitrogen and a formal negative charge on oxygen is an indication that this resonance structure contributes less to the ground state structure of NO2 than the previous one, with the unpaired electron on oxygen.
And so here we have 2 resonance structures. So you have the same set of atoms, same arrangement of the atoms, but you're just putting the electrons in a slightly different place. And so that would correspond to a resonance structure. Now we have 2 resonance structures. In one case, we have the single electron on the nitrogen. In another case, the single electron is on the oxygen. And the question is, what's the more stable? And so if we calculate the formal charge, here oxygen 6 minus 2, 4, 6, 0. Nitrogen 5 minus 2, 4, 5, 0. 6 minus 2, 4, 5, 6, 0. And so this one on the left all have 0 formal charges. 6 minus 2, 4, 6, 0. 5 minus 1, 2, 3, 4. 5 minus 4 is +1. 6 minus 2, 4, 6, 7 gives us a -1. And so the one where everything is a 0 formal charge should be more stable. And so that tells us this is the predominant resonance structure. Remember that the actual structure is going to be a weighted average of the resonance structures, meaning that the more stable resonance structure will contribute more to the actual structure. Now it's kind of cool. Using the formal charge, we could actually determine what is the most stable local environment for an atom. So boron starts with 3 valence electrons. If it's surrounded by 4 single bonds, that would be 3 minus 4 gives us a -1 formal charge. 3 minus 1, 2, 3, 4, 5, that would give us a -2. 3 minus 2, 4, 6. minus 3, minus 4 formal charge. Now here we have 3 single bonds. 3 minus 1, 2, 3 gives us a 0 formal charge. Minus 1, minus 1, and minus 1. And so we'd say that the most stable local environment for a boron would be the boron with the 3 single bonds. Now, it doesn't have an octet, and this is an exception to the octet rule, right? So some boron and aluminum are often happy with just 6 valence electrons, 3 single bonds, and we understand that based on having a 0 formal charge. We can do the same thing for carbon. Carbon starts with 4 single bonds, 4 valence electrons, minus 1, 2, 3, 4, and so that would give a formal charge of 0. 4 minus 5 gives you minus 1, minus 2, and the farther from 0 the formal charge, the less stable. And so we'd say when formal charge is 0, that's the most stable, minus 1 a little bit less stable, minus 2 even less stable than that. And so doing this, we see that these are the 4 most stable structures for carbon, or most stable local environments for carbon. And so typically carbon does not want a lone pair. Now notice down here, this is the environment that carbon has in carbon monoxide. And so there are exceptions. That triple bond is probably why carbon monoxide looks like that. But when you're doing Lewis diagrams, you might want to keep these at the back of your mind, and it'll make doing Lewis diagrams a little bit easier. If we do nitrogen, nitrogen starts with 5 valence electrons. And so 5 minus 1, 2, 3, 4 gives us plus 1. 5 minus 5 is 0. And so we can determine the formal charges for all of these. And so we see for nitrogen, these are the environments that it prefers. It's kind of interesting. Nitrogen wants a lone pair of electrons. We can do the same thing for oxygen. And oxygen starts with 6 valence electrons for the free atom. Now these are the most stable structures for the oxygen. Typically you're going to have 2 single bonds, 2 lone pairs, or 2 lone pairs and that double bond. And so often when I'm doing Lewis diagrams, I'll keep this in the back of my mind, and it just makes it a lot easier. And so these are the most stable structures for these elements. For fluorine, in all compounds, fluorine will have 1 single bond and 3 lone pairs. That gives it a formal charge of 0. And again, for the boron, it's surrounded by just 6 valence electrons. But based on the formal charge, we know that's fairly stable. And so one of the exceptions to the octet rule is that boron and aluminum are often happy with just 6 valence electrons. We can do the same thing for sulfur. Sulfur starts with 6 valence electrons. 6 minus 1, 2, 3, 4 gives us a 2. 6 minus 5, 1. 6 minus 6, 0. And so for sulfur, we see that this is a stable configuration, this is a stable configuration, this is a stable configuration. Now notice that sulfur is surrounded by 2, 4, 6, 8, 10 valence electrons. And so another exception to the octet rule is that elements in the 3rd row and lower can be surrounded by more than 8 electrons, and sulfur is in the 3rd row. We can do the same thing with xenon. Xenon's free atom has 8 valence electrons. And so again, here we find the 2 of the stable structures for xenon. In this one, xenon is surrounded by 2, 4, 6, 8, 10. But again, elements in the 3rd row and lower can have more than an octet. And so xenon is below the 3rd row. In this one, xenon is surrounded by 2, 4, 6, 8, 10, 12. And again, that's okay because we see that we have a formal charge of 0. So we can understand the exceptions to the octet rule, to the noble gas rule, based on formal charges. And so those are most stable configurations for sulfur or xenon. If we look at carbon dioxide, it's kind of interesting. We typically put carbon in the middle, but how do we know that's more stable than putting oxygen in the middle? Or how do we know having 2 double bonds is more stable than a triple and a single bond? in this case, everything has an octet, has noble gas configuration. In this case, everything has noble gas configuration. But with the two double bonds, we see we have a formal charge of 0. With the triple and a single, we see that we have a formal charge of +1 and -1. And so these two are resonance structures. The actual structure is a weighted average of the resonance structure. And so the actual structure should look more like the one with the two double bonds based on the formal charges. And again, here is the question, so how do we know carbon's in the middle, not in the end, and not oxygen in the middle? And so again, all these have noble gas configuration. We use the same number of valence electrons. We can calculate the formal charges. And so based on the formal charge, we see that the carbon should be in the middle. That's a more stable isomer than having carbon not in the middle. So you can use formal charge to determine which is the predominant resonance structure. You can use formal charge to determine what is the more likely isomer. And again, isomers, you have the same set of atoms but a different arrangement. So having carbon in the end or versus the middle gives you two isomers. We can ask what's the most stable structure for N2O. Should the nitrogen be in the middle or the end? Or should the oxygen be in the middle? And so we can draw some of the structures, and then we can figure out the formal charges. Remember, so nitrogen starts with 5. 5 minus 2, 4, 6 gives us a -1. 5 minus 4 plus 1. 6 minus 2, 4, 6 gives us a 0. Now, these ones with 2 are not going to be very structured, very stable at all. And so we're now going to be looking at these two. There should be the most stable of these 5. Now we can even take one step further. If you have a negative formal charge, it should go on the most electronegative element. And so oxygen is the most electronegative element of these two. And so it should have the negative formal charge. And so this resonance form should be more stable than that one. So please remember, negative formal charges should go on the most electronegative. Positive formal charges should go on the least electronegative. We could also ask what's the most stable Lewis diagram for sulfur dioxide. So assuming sulfur is in the middle, do we have a single and a double or two doubles? Now based on noble gas, we'd say, well, the one on the left should be more stable. Based on formal charge, the one on the right should be more stable. Remember, elements in third row and lower can have more than 8 valence electrons. And so we'd go with the one on the right. Also, remembering that oxygen formal charge 0 corresponds to a double bond, 2 lone pairs, you can actually start with this configuration. We could also ask about sulfur trioxide, assuming sulfur is in the middle. So we could have 1 double bond, 2 lone pairs, two singles, 2 double bonds, 1 single, or 3 double bonds. Now the one on the left is the only one with everything having noble gas configuration. But if we do the formal charge, so in this case, these oxygen have a -1 formal charge. The sulfur would be 6 minus 4, a +2. And so based on formal charges, this should be the least stable. Based on formal charges, this is going to be a little bit better. And based on formal charges, this is the most stable. And so here we got 3 resonance structures. Again, resonance structures, you only differ by where you put the electrons. And the actual structure should look mostly like this one here, where all the formal charges are 0. And again, elements in the third row lower can have more than 8 valence electrons. And so we can understand the exceptions to the octet rule based on formal charges. We saw that elements in row lower often have more than 8, so we saw that with xenon and sulfur. Boron and aluminum sometimes have only 6 valence electrons, and we saw that with 3 single bonds, boron would have a formal charge of 0. So hopefully you can determine oxidation states and formal charges of atoms and molecules. You should be able to use formal charge to determine which resonance structure and which isomer is the most stable. You can use also formal charge to understand why there are exceptions to the octet rule. I hope that was helpful.